Okay, so on number 1, I've got a building that was moved. Entire hotel building was moved several blocks on dollies. Mass of the building was 1.45 times 10 to the 6 kilograms. 1 times 10 to the second megajoules of work was done to overcome the force of resistance, which was 2% of the building's weight. How far was the building moved? Well, we've got a whole lot of nested stuff in here. So the first thing we have to find out, I guess, is the force, the net force on the building. So if we start off, I'm going to set that aside. We know we want distance, so we're going to have to come back to this work formula. I know that the force of friction, I guess I should label it force of friction, force of resistance is what they call it, is 2%, so 0.02 times mass gravity. And so force of friction equals 1.45 times 10 to the 6th kg times 9.81 meters per second squared times 0.02. How many of you did 2% of the mass, not the... Yeah. Don't mix up mass and weight. Weight is Fg, mass gravity. That's a pretty common mistake on this one. So I get a force of friction of 2844900 joules. From there, it's pretty straightforward. You also had to do a conversion because the work was given to you in megajoules. So 100 megajoules, 1 times 10 to the second megajoules is equal to 1 times 10 to the 8th joules, which is a really unwieldy number. I mean, there's a good reason for using scientific notation there. And so then we can just take this and say, well, work divided by force is equal to the distance. The force applied is going to be in the same direction as the work being done. So it's cosine of 0, so I just sort of dropped that, because that's just going to give you a 1. Work, 1 times 10 to the 8th joules, divided by my 2844900. Oh, gosh, I put that in joules. Goofball. Newtons. Gives you the distance. Can you get that number now? So many of you use the mass, not the weight. How many of you also forgot to convert your megajoules to joules?
I just forgot the size of megajoules. Yeah, I said 5.
Oh, okay, well that's good. I saw some decimal errors. Hey, I stand corrected. I have an extra 0 there, so let's scrub that. So that gets us 35.2. Sorry. I got 0 excited.
So, in case of 0 out, it's still 351.
It wouldn't change the numbers, it would just change the decimal location.
No, if there was an
it's
extra 0,
351.
it would be
With the 0 that you have, it's 35. So you took 0.
Oh. You know what? That's because I probably screwed up my key the first time and I fixed the end result, but I didn't fix all the intermediate steps. My apologies. I don't even understand how I'm wrong. Okay. Yeah, you're right.
Wait, what's going on here?
Nothing. Ignore it. Go back to sleep. That was a joke. It's 352. I screwed up on my own key when I made this key, and I had a decimal error the first time, and I know exactly what I did. I put in 2% as 0.2, not 0.02. So, because my first line, I looked at it and I was like, oh, I got 0.2. Oh, I fixed it in the next step. Well, apparently I didn't fix it everywhere. So, sorry. It is 352 meters. So, they didn't move it all that far, but that's a long distance for something very, very heavy. Okay, any other questions or any other mistakes that I've made? You good? Okay, let's go to number 2. Okay, so we've got this box. It's being pulled up the ramp. We are given a distance. We are given an initial velocity. We're given a mu k. We're given mass. And the first question we're asked is how much work is done by friction? So the first thing we want to write down is that the work of friction is equal to the force of friction times the distance the box has moved times the cosine of theta, where theta is the angle between the force of friction and the motion of the box. So let's address a couple things. We have distance, it's the 6.5. What's our cosine theta going to be here? 180. So that'll be cosine 180 because friction is working opposite the motion of the box. So we have to find the force of friction. Well, to do that, we need some sums of forces here. So sum of forces on the, I'm going to go ahead and start with sum of forces on the y. Why? Because I can. It's equal to 0, and it's equal to the normal force minus force of gravity on the y. That'll get us our normal force. So normal force equals, well, if we kind of zoom in here, gravity on the y will be force of gravity cosine theta. So normal force equals mass gravity cosine theta. And because we were given mu k equals Fk over Fn, which gives us a really easy solve. We didn't have to do a sum of forces on the x. Mu k Fn equals Fk. We can just plug that in right here. Work done by friction equals mu k Fn times distance times cosine 180. We know that Fn equals mg cosine theta, so work done by friction equals mu k mg cosine. Be careful because you've got two different angles here. Oh. So mu k mg cosine theta times distance times cosine of 180. So that'll get you your work done by friction. And it is negative, I forget what the raw answer is. The final answer is negative 690 joules. It's opposing the motion of the box as friction does. I think friction has oppositional defiant disorder. Yeah, it wasn't all that funny. Okay, so the next part of this is what's the change in kinetic energy of the box over the distance that it is pulled. So delta KE, well, there are a couple different ways to skin this particular cat. We can do delta KE equals the net work, which means it equals the net force times the distance times cosine theta. We're told that the box is moving up the slope, so that would be fairly straightforward. We could do delta K equals work net equals work of the puller minus work of gravity minus work of friction. Either way, we're going to have to find those forces because work of the puller is just force of the puller times distance. So, I found it simpler to just find net force. So I'm going to say that net work equals, well, force of the puller is given. I guess should I back up a step and do the sum of forces on the x-axis? Yeah, let me do that. My apologies. How do we find that net force? Well, we know that the motion is all on the x-axis. Therefore, sum of forces on the x is equal to the net work being done. And that sum of forces on the x also, let me shrink this up, is going to equal force of the puller, force applied, I guess I had it labeled, minus force of gravity on the x minus force of kinetic friction. So I've already got an expression for force of kinetic friction. And the force of the puller was given. I just needed an expression for force of gravity on the x. So force of the puller minus mg sine theta minus mu k mg cosine theta. So that gives me my expression for net force, and I can take that whole mess, and it is a bit of a mess, I agree. Copy, paste. Times d times cosine 180, or I'm sorry, cosine 0. Does that seem reasonable? How many of you tried some approach like this? Okay. What were the trip ups?
I don't know.
Okay.
I had that exactly.
You have that exactly. Would you,
At first I didn't account for gravity, but then whenever we were discussing, we did it again, I reworked it with accounting for gravity, and I still got 2.3 times.
oh yeah, that's right. That's right. We have a small disagreement here. Okay. So let's look at that, because I can be wrong. I'm wrong plenty of times. Force of the polar is 3730. Is that correct? 3730 newtons minus. Could I simplify this at all? I could do this. Mass gravity times sine 16 plus mu k cosine 16 times distance times cosine 0. Okay, let me put some numbers in there. Okay, so I do get 20 sig fig to 2,300 joules. Sorry about that. I don't know what I did. I'm gonna have to go back and look at my calculations. Yeah. Okay. So with my correction, how many of you had it? Okay. Did you have it the first time?
Yeah.
Okay. Okay. So that's my fault. I'll go back and fix those. All right. I'm gonna break this video here, and then let's do 4. Do we need to do 4 and 5?